4 countries, 4 independent telescopes, 1 interstellar visitor, 1 feature that appears in every single image. And here's what makes this impossible. These astronomers don't know each other. They're using different equipment, different software, different hemispheres, different time zones. Yet they're all capturing the same thing, a geometric pattern in the coma of 3I Atlas that is highly unusual compared to typical comets. Spain processes their images on November 22nd and sees it. Thailand reports similar features. Japan's amateur networks report consistent patterns. US observer AstroPhotoG photographed similar features in October, and only now is anyone realizing what they caught. This isn't one controversial photograph that everyone's debating. This is multiple independent observations converging on a singular, unexplained phenomenon, and the most unsettling part? NASA's official images released after a government shutdown delayed their analysis show something too, but their version showed less structural detail than amateur ground images. You're about to see something that has scientists reconsidering everything they thought they understood about interstellar objects. Because when amateur astronomers across the globe start outperforming billion-dollar space telescopes, when backyard observers are providing data that professional institutions either can't or won't clarify, we're not just looking at a scientific anomaly anymore. We're looking at a verification crisis. And at the center of it all is an object that's been traveling through interstellar space for potentially millions of years, only to arrive in our solar system and begin behaving in ways that challenge our fundamental models of how comets work. Stay with me, because in the next few minutes we're going to examine the actual images from Spain, Thailand, Japan and the United States. We're going to compare them side by side. We're going to look at what NASA released and ask the questions that thousands of amateur astronomers are already asking in private forums and research communities. We're going to explore why Harvard astrophysicist Avi Loeb, the same scientist who proposed that Oumuamua might have been artificial, is now watching 3I Atlas so closely that he's published multiple detailed analyses in the span of just days. And we're going to discuss why this object is currently sitting at level 4 on something called the lobe scale, which measures how unusual an astronomical object is, and whether the evidence we're about to examine may approach level 5, where technological origin becomes worth mathematical consideration. This isn't about jumping to conclusions. This is about looking at what's actually in the images. Because right now, 3I Atlas is still visible in our night sky. It's moving through space at tens of thousands of miles per hour. It passed its closest approach to the Sun back on October 29th, and many comets fragment post-perihelion, but this survived intact, that it should be showing a normal chaotic outgassing pattern, that its tail should be pointing directly away from the Sun like every other comet we've ever studied. But that's not what the images show. They show structure, they show geometry, they show rotation patterns that persist across multiple observation nights. And they show something even stranger, a plume of material pointing toward the Sun, an antitail that challenges typical solar radiation pressure expectations. When one telescope captures something unusual, we call it an artifact. When 2 capture it, we call it interesting. When 4 independent observers across multiple continents capture the same feature using different equipment and processing methods, we stop calling it an artifact and start calling it a pattern. And patterns demand explanation. So either every amateur astronomer who pointed a telescope at 3I Atlas in late October and throughout November experienced the exact same optical malfunction, the exact same processing error, the exact same misidentification of what they were looking at, or 3I Atlas is exhibiting behavior that our current models of cometary physics struggle to account for. This is one of those moments where citizen science is moving faster than institutional science, where the distributed network of amateur observers around the world, sharing data freely, processing images transparently, is producing results that demand attention. And the establishment is paying attention. Loeb certainly is. But the public conversation hasn't caught up yet. The mainstream coverage has been minimal. The images circulating in astronomy forums haven't made it to broader audiences. That's what we're changing right now. So here's what I need from you. Drop a comment telling me where you're watching from, because this object is visible from your hemisphere right now, and if you have access to even a modest telescope, you can verify what we're about to discuss with your own observations. Geographic verification matters here. This isn't about taking someone's word for it. This is about independent confirmation from as many observation points as possible, and if you're watching from Spain, Thailand, Japan or the United States, I especially want to hear from you because you're in the regions where these breakthrough images originated. Hit that like button if you're ready to examine evidence that mainstream coverage isn't showing you yet, and let's begin with the context you need to understand why these images matter so much. Because before we can appreciate what's strange about 3i Atlas, we need to understand what it was supposed to do, and why its refusal to follow the script is making some of the world's most careful scientists reconsider their assumptions about what's possible in our solar system. Let's establish something fundamental first. When we talk about comets, we're talking about objects we understand extremely well. We've been observing them for thousands of years. We've sent spacecraft to them. We've landed probes on their surfaces. We know their composition. Water ice mixed with dust, organics, frozen gases. We know their behavior. As they approach the sun, solar heat causes their ices to sublimate, creating the characteristic tail and surrounding cloud of gas and dust called a coma. We know their fragility. They frequently break apart under thermal stress or gravitational forces. Comets are, in astronomical terms, predictable. 3i Atlas was supposed to be predictable too. It was confirmed as an interstellar object, meaning it originated outside our solar system, but the working assumption among most astronomers was that it would behave like a comet despite its exotic origin. Why? Because its trajectory, its spectroscopic signature, its apparent composition all suggested comet-like characteristics. Yes, it came from another star system, which makes it inherently fascinating. It formed in conditions we can only infer around a sun we'll never observe, potentially billions of years ago. But the expectation was that the fundamental physics would be the same. Solar radiation pressure would push material away from the sun. Thermal stress as it approached perihelion would either cause fragmentation or trigger predictable outgassing patterns. Its orbit would be governed purely by gravity and momentum. It reached that perihelion point, its closest approach to our Sun, on October 29th. This is the moment of maximum thermal stress for any comet. This is when fragmentation typically occurs. This is when tails grow most prominent. This is when observational astronomy gets most interesting, because the increased activity reveals the comet's internal structure and composition. So astronomers around the world pointed their instruments toward 3i Atlas, expecting to document a relatively standard show. An interstellar comet behaving like its solar system cousins, just with a more exotic backstory. That's not what they saw, and it's not what they're still seeing now, weeks after perihelion passed. The object persists, its structure remains coherent. And instead of the chaotic, asymmetric, random outgassing that characterizes typical comet comas, multiple observers started noticing something geometric, something organized, something that repeats across rotation periods. Now, before we go further, let's be clear about what this means scientifically. Strange doesn't automatically mean artificial. Nature produces complex patterns all the time. Snowflakes have geometric precision. Crystals grow in organized lattices. Planetary rings show structure. The universe is full of order emerging from natural processes. So when we say 3i Atlas is behaving strangely, we're not immediately jumping to extraordinary conclusions. We're saying its behavior doesn't match our models, and that gap between expectation and observation is where scientific investigation begins. This is where Avi Loeb enters the conversation more prominently. You probably know Loeb as the Harvard astrophysicist who suggested Oumuamua, the first confirmed interstellar object discovered back in 2017, might have been artificial, or at least exhibited characteristics that technological origin could explain better than natural explanations. That hypothesis was controversial. Many in the astronomical community pushed back hard, arguing that natural explanations, however unlikely, should always be preferred until evidence absolutely demands otherwise. Loeb's counter-argument has always been that science should follow the data wherever it leads, that dismissing possibilities prematurely is itself unscientific, and that the burden of proof works both ways. Natural explanations also need to account for all the observations, not just the convenient ones. Loeb has developed what he calls the Loeb scale, a framework for evaluating how anomalous an astronomical object is. Think of it as a structured way to assess unexplained phenomena without immediately polarizing into its nothing versus its aliens camps. The scale has 5 levels. Level 1 represents conventional objects behaving exactly as expected. Standard comets, asteroids, planetary bodies. Level 2 covers objects with minor oddities that are easily explained within current models. Level 3 indicates more significant anomalies that prompt discussion but don't fundamentally challenge our understanding. Level 4 is where things get interesting. It represents an anomaly requiring serious further investigation, where multiple unexplained behaviours start stacking up, where natural explanations become increasingly strained even if still plausible. And level 5 is the threshold where an object meets potential technosignature criteria, where the possibility of technological origin becomes mathematically non-negligible, where the scientific community needs to seriously consider hypotheses they'd normally dismiss. Right now, Loeb has placed 3i Atlas at level 4. That's significant. That's not casual speculation. That's a serious scientist with institutional credibility saying this object's behaviour is sufficiently anomalous to warrant dedicated investigation beyond standard astronomical observation. And based on the images we're about to examine, there's a real question about whether it crosses into level 5. That's not a question Loeb, or any responsible scientist, answers lightly. Because level 5 carries implications that go far beyond one unusual comet. It opens conversations about non-human technology, about intentional observation or exploration of our solar system, about the possibility that we're not looking at a passive chunk of ice and rock, but something with purpose. Those conversations are uncomfortable for many scientists, and understandably so. The history of false positives in the search for extraterrestrial intelligence is long and embarrassing. Nobody wants to be the person who cried alien over a natural phenomenon misunderstood. But here's the thing, and this is crucial to understanding why this story matters. Loeb isn't some fringe figure making wild claims on YouTube. He's published hundreds of peer-reviewed papers. He's chaired Harvard's astronomy department. He's advised NASA. He's one of the most cited astrophysicists in the world. When he says something is anomalous, the scientific community might disagree with his interpretations, but they can't dismiss the observations he's highlighting. And with 3i Atlas, he's not alone in noting the strangeness. Amateur astronomers who have no stake in controversy, who just want to capture beautiful images of space, are independently reporting the same features Loeb is analysing. So why does this object matter more than Oumuamua or Borisov, the second interstellar visitor? Because with Oumuamua, we only had sparse data, a few observations as it was already leaving the solar system, moving too fast for us to get detailed imaging or spectroscopy. With Borisov, it behaved almost boringly normal, a textbook interstellar comet that acted exactly as expected. It was exciting because it was from interstellar space, but it didn't challenge our models. 3i Atlas is different. We're catching it at the right time, with better observation windows, with more advanced equipment in amateur hands, and it's not following the script. It's visible for months, not days. We're getting detailed spectroscopy. We're capturing high-resolution images from multiple angles, and all that data is painting a picture that doesn't quite fit. The establishment response has been mixed. NASA organised a virtual event on November 18th and 19th to share their observations from professional instruments. Hubble Space Telescope, James Webb Space Telescope, even Mars orbiters that caught views of 3i Atlas during its perihelion approach. But that release was delayed by a government shutdown that ran from early October through mid-November, and when the images finally came out, they were disappointing to many observers, not because they showed nothing, but because they showed less than what amateur astronomers had already captured and shared in online communities. The professional images were blurrier, less detailed, more ambiguous, and that ambiguity, combined with the delayed release, created exactly the kind of information vacuum that conspiracy thinking thrives in. To be fair to NASA, there are legitimate technical reasons why space-based telescopes might produce less detailed images of 3i Atlas than ground-based observations. Observation windows, solar conjunction limiting viewing angles, the object's distance and relative motion, all these factors affect image quality. But the optics of the situation are undeniable. Billion-dollar space telescopes underperformed compared to backyard observers with mid-range equipment. That's a public relations nightmare for an institution that depends on demonstrating value. And it's a credibility boost for the citizen science community that's been arguing for years that distributed observation networks can sometimes outperform centralized institutional approaches. The conversation around 3i Atlas right now exists in this weird space between institutional caution and grassroots curiosity. Professional astronomers are watching it carefully, publishing data, running analysis, but they're hedging their language, emphasizing uncertainty, avoiding any statements that might be misinterpreted as endorsing exotic explanations. Amateur astronomers, meanwhile, are sharing images freely, discussing anomalies openly, and asking the questions that sound too speculative for academic papers, but are exactly the questions any curious person would ask. And scientists like Loeb are trying to bridge that gap, bringing academic rigor to unconventional questions, willing to stake their professional reputation on saying, this is worth investigating seriously, even if it makes us uncomfortable. That's the context we're operating in. This isn't a story about one photograph or one scientist's interpretation. This is a story about convergence. Multiple independent observations pointing towards something unexpected, creating enough signal through the noise that dismissing it requires active effort. And now we're going to look at those observations directly, starting with the images that came out of Spain in late November and sparked this entire conversation. On November 22nd, an astronomer operating under the name Astronomy in Spain processed images of 3i Atlas captured over several nights of observation. These weren't casual snapshots. This was careful astrophotography, long exposures, precise tracking, proper calibration, the kind of methodical imaging that amateur astronomers at the advanced end of the hobby have perfected. Ray wasn't looking for anything anomalous specifically. The goal was documentation, contribution to the observational record, maybe capturing some beautiful views of an interstellar visitor. What showed up in the processed images wasn't beautiful. It was strange. The coma, the cloud of gas and dust surrounding 3i Atlas's nucleus, displayed what Ray described as dual clockwise wave patterns. Not random, not chaotic, not the sort of irregular, turbulent structure you see in typical cometary outgassing. These were organized rotational patterns visible in the gas distribution, two distinct wave systems both rotating in the same direction, persisting across multiple observation periods. If you've ever seen time-lapse footage of weather systems rotating around a storm center, or water flowing in spiral patterns down a drain, you have a mental image of what we're talking about. Except this is happening in the coma of an interstellar comet, in the vacuum of space, where there's no atmospheric physics to drive such organization. Ray documented this across images taken on consecutive nights. The pattern persisted, the geometry held, the rotation appeared consistent with a specific period, suggesting that whatever was generating this structure was tied to the object's spin. In normal comets, you sometimes see jets, localized outbursts of gas from active regions on the nuclear surface, often triggered by subsurface pockets of volatile material suddenly exposed to solar heating. Those jets can create asymmetries in the coma. They can produce plumes or fans of material, but they're typically irregular, short-lived, and they don't organize into coherent rotation patterns that last for days. What Ray was seeing looked different. It looked organized. Now, let's be careful here. Human brains are pattern recognition machines. We see faces in clouds. We see geometry in randomness. This is called pareidolia, and it's a well-documented cognitive bias that affects everyone, including trained scientists. So when an amateur astronomer says they're seeing structure in a fuzzy cloud of gas around a distant comet, the first question should always be, are you seeing actual structure, or are you imposing pattern recognition onto noise? That's a fair skeptical question. And it's exactly why the processing methodology matters. Ray wasn't just eyeballing the images. The processing involved standard astrophotography techniques, stacking multiple exposures to reduce noise, applying enhancement filters to bring out faint details, using edge detection algorithms to highlight boundaries and gradients. These aren't subjective processes, they're computational. And when those computational methods consistently reveal the same geometric features across independent image sets from different nights, the pattern recognition explanation becomes less convincing. You're not looking at one ambiguous image where people might see different things. You're looking at multiple processed datasets all showing consistent structural elements. The specific features Ray highlighted included a central void region, an area of notably lower density in the coma, positioned asymmetrically relative to where the nucleus should be. Around that void, the gas distribution showed what appeared to be two spiral wave patterns, both rotating clockwise when viewing the object from a specific angle. The waves weren't perfectly defined like a spiral galaxy's arms, but the suggestion of rotation was clear enough that multiple people examining the images independently described the same feature without prompting. That's an important validation step in citizen science. When observers looking at the same data without coordination arrive at similar descriptions, It suggests they're responding to actual signal, not interpreting noise. But the most compelling aspect wasn't just the structure itself, it was the persistence and evolution. Over the 3 nights Ray imaged 3i Atlas in this period, the pattern rotated. The specific position of the features changed in a way consistent with the object spinning. If this were purely a processing artifact or a random fluctuation in the gas, you'd expect it to look different each night, to shift unpredictably, to lose coherence. Instead, it behaved like a stable structure rotating with the object. That's behaviour you'd expect from something physically anchored to the nucleus, not from random outgassing turbulence. Ray published these images to amateur astronomy forums, and the response was immediate. Other observers started examining their own images of 3i Atlas from around the same time frame. Some had captured similar features but hadn't initially processed their data to bring them out. Others began planning new observation sessions specifically to verify or refute what Ray had documented. And Avi Loeb, who monitors these communities specifically because they often provide data before professional publications, saw the images and started his analysis. Loeb's November 22nd through 25th Medium posts. He publishes frequently there to communicate with broader audiences beyond academic journals, focused on these Spanish observations. His analysis emphasized that dual spin wave systems are not documented in any historical comet observation. He reviewed the literature, centuries of comet studies, thousands of objects, extensive datasets from both professional and amateur sources. Asymmetric jets, common, fan-shaped plumes, well documented, rotating spiral structures, essentially absent. When comets show rotation-related features, they typically manifest as regularly spaced jets, or repeated asymmetries, not as organized wave patterns in the coma gas. Why does this matter scientifically? Because the physics of cometary outgassing is supposed to be chaotic. You have solar heating driving sublimation of surface ices, but that heating is uneven because the nucleus is irregularly shaped with varying composition across its surface. Some areas are more active than others. Some ices are more volatile than others. The gas escaping doesn't flow smoothly. It erupts, it pulses, it responds to the changing solar angle as the object rotates. All of that should produce turbulence, not organization. The fact that 3i Atlas appears to show organized structure suggests something about its interior or rotation is unusual. One natural explanation that scientists immediately considered was that we might be viewing the object from a specific geometric angle, where normal jets happen to create the illusion of rotation patterns, a perspective effect essentially. If you have a few active jets on the nucleus, and you're viewing from just the right angle, maybe they create a pattern that looks more organized than it really is. That's plausible for a single observation. But it becomes less plausible when the pattern persists across changing viewing geometries as the object moves and Earth's position changes, and especially when other observers from different locations report similar features. The spectroscopic data added another layer to this puzzle. During the same period that Ray was capturing these images, other observers were conducting spectroscopy, analyzing the light from 3i Atlas to determine its chemical composition. What they found was unusual. The gas in the coma was dominated by nickel vapor, with notably absent or very weak iron signatures. That's bizarre. In typical solar system comets, when you see metal emission, iron usually dominates, or at least appears alongside nickel. They're chemically similar, often found together in cosmic material. Finding strong nickel with weak iron suggests something unusual about 3i Atlas's formation conditions or composition. Why does composition matter for understanding these rotation patterns? Because the material properties of the nucleus affect how it fragments, how it outgasses, how it responds to thermal stress. A nickel-rich composition would make the nucleus denser, more structurally coherent, less prone to chaotic fragmentation. If the object is more mechanically solid than a typical comet, then its rotation might drive more organized outgassing patterns, material released from specific active regions as those regions rotate into sunlight, creating a rhythmic pattern rather than random turbulence. That's still a natural explanation, but it requires 3i Atlas to have an unusual internal structure compared to normal comets. There's also the timeline to consider. Ray's observations came just 3 weeks after perihelion. That's when thermal stress should be maximum, when fragmentation is most likely, when activity should be chaotic and intense. Instead, 3 weeks post-perihelion, the object was showing structural coherence and organized patterns. Most comets that survive perihelion are settling down by that point, their activity declining as they move away from the Sun. 3i Atlas was still active enough to produce these patterns, but organised enough that they were visible and consistent. That combination, sustained activity with maintained structure, is difficult for standard comet models to explain. Ray's discovery didn't prove anything. One observer's images, no matter how carefully processed, don't constitute definitive evidence of anything extraordinary. What they did was establish a hypothesis. 3i Atlas might be exhibiting structural features in its coma that are highly atypical. And that hypothesis was immediately testable. Other observers could point their telescopes at the same object and see if they found the same features. That's exactly how citizen science should work. One person makes an observation, shares it transparently, and invites verification or falsification from the community. What happened next was verification, and that's what transformed this from an interesting oddity into a compelling pattern that demands explanation. When Ray's images circulated through amateur astronomy communities in late November, the immediate response from skeptics was predictable and reasonable: processing artifacts, pareidolia, isolated observation from one location. These are the standard explanations that need to be ruled out before taking any anomalous observation seriously. But ruling them out requires independent verification. Other observers, other equipment, other locations, ideally observing at different times. If multiple independent observers see the same features, the artifact explanation collapses. If they're all seeing different things, the pareidolia explanation wins. The test was straightforward. What do other telescopes show? Thailand provided the first independent report. An observer there, working with different equipment than Ray, different telescope design, different camera, different image processing software, captured 3i Atlas during overlapping timeframes with Ray's observations. The Thai images weren't identical to Ray's, which would actually have been suspicious. They showed the object from a slightly different angle because of geographic location. The exposure times were different, the resolution was different, but the essential features were present: geometric boundaries in the coma gas, suggestion of rotational structure, the same asymmetric density distribution with a notable void region. This wasn't someone copying Ray's work or unconsciously mimicking his interpretation. This was independent observation finding consistent features. Japan's amateur networks and Japanese amateur astronomy is remarkably sophisticated, with extensive coordination and data sharing among hobbyists, began targeted observation campaigns specifically to verify or refute the Spanish and Thai findings. Multiple observers across Japan pointed their telescopes at 3i Atlas over several nights in late November. They used a variety of equipment: refractor telescopes, reflectors, Schmidt-Cassegrains, different aperture sizes, different camera sensors. The processing methods varied. Some used automated stacking software, others did manual alignment and processing. Despite all that variation in methodology, the consensus from the Japanese observation network was clear. Something unusual was visible in the coma structure. Descriptions consistently mentioned geometric appearance, rotation, adjusted patterns, a symmetry that didn't match typical comet behaviour. Now here's where this gets particularly interesting from an evidentiary standpoint. The observations from Spain, Thailand and Japan were happening in late November, and the astronomy community was starting to buzz with discussion about 3i Atlas's strange appearance. But then someone went back through earlier observations and found something critical. An observer in the United States operating under the name US amateur AstroPhotoG captured October images showing similar coma features more than 3 weeks before Ray's discovery using a Dobsonian reflector telescope. At the time, AstroPhotoG had processed the images for basic viewing, but hadn't examined them with the kind of detailed enhancement that would reveal subtle coma structure. When Ray's findings prompted a re-examination of that October 21st data, the features were there. The same void region, the same geometric boundaries, the same suggestion of organised structure. This is profoundly important. This wasn't a case of everyone jumping on a bandwagon after one person claimed to see something, with confirmation bias driving subsequent observers to see patterns that weren't really there. This was a case where the pattern existed in data captured before anyone knew to look for it, and only revealed itself when proper processing was applied retroactively. That's about as bulletproof as verification gets in observational astronomy. You can't fake data that was timestamped and archived weeks before the hypothesis even existed. Let's think about the statistical improbability of what we're discussing. We're saying that observers in Spain, Thailand, Japan, and the United States, separated by thousands of miles, observing from different hemispheres, using different equipment from different manufacturers, employing different processing software with different algorithms, all independently captured the same anomalous features. The odds of all of them experiencing identical optical artifacts are vanishingly small. Optical artifacts are specific to the equipment that produces them. Vignetting, the darkening at image edges, depends on your telescope's focal ratio and camera sensor size. Diffraction spikes, the star-like patterns around bright objects, depend on whether your telescope has a secondary mirror support structure in its design. Atmospheric distortion varies with local weather conditions and altitude. There's no mechanism for observers using completely different equipment in different atmospheric conditions to produce identical artifacts. The processing artifact explanation is equally implausible. Yes, certain enhancement filters can create artificial structure if applied inappropriately. Edge detection algorithms can highlight noise and make it look like boundaries. But these effects are predictable and recognizable to experienced astrophotographers. When someone oversharpens an image, it looks oversharped. You get characteristic halos and ringing artifacts around bright features. When someone applies edge detection too aggressively, you get pixelated false edges that don't correspond to actual features. The images we're discussing don't show those telltale signs of processing errors. They appear to reveal genuine structural features through appropriate enhancement techniques. And here's another critical point. These observers weren't trying to find anything unusual. They were just imaging an interesting interstellar object. AstroPhotoG in October certainly wasn't hunting for anomalies. The conversation about Three-Eye Atlas being strange hadn't started yet. The Thai observer was doing routine astrophotography. Even Ray, whose initial findings sparked this discussion, was just trying to get good images for documentation purposes. Nobody was going into this with the intent to prove something extraordinary. They were doing normal astronomy, and the features showed up anyway. The astronomy community has developed informal methods for validating unusual observations, precisely because false positives and processing errors are so common. One method is the diversity of equipment test. If a feature is real, it should be visible across different types of telescopes and cameras. Three-Eye Atlas's coma structure passed that test. Another method is the temporal consistency test. If a feature is real and tied to the physical object rather than observation conditions, it should evolve predictably across observation sessions as the object rotates and moves. The features in Three-Eye Atlas pass that test too. They change position and orientation consistent with rotation, rather than appearing random and different each time. A third validation method is the blind observation test. Show images to multiple people without telling them what you think you see, and check if they describe the same features independently. Several astronomy forums ran informal versions of this test, posting the enhanced images of Three-Eye Atlas without commentary, and asking participants to describe what they observed. A significant majority mentioned geometric appearance, structural features, asymmetric patterns. That's not absolute proof. Human visual cognition does have biases that make us see patterns, but it's supportive evidence that the features are prominent enough to register across multiple observers. The skeptical counter-argument at this point became more sophisticated. Instead of claiming artifacts or misinterpretation, skeptics argued that the features might be real but still naturally explainable through unusual but not unprecedented comet behavior. Maybe Three-Eye Atlas has an exceptionally strong single jet that's creating the appearance of structure. Maybe its rotation axis is oriented such that we're seeing Polion view, which could create unusual symmetries. Maybe subsurface cavities are collapsing in patterns that create rhythmic outgassing. These are more credible objections because they acknowledge the observations while proposing natural mechanisms. But each of those explanations faces challenges when confronted with the full dataset. A single strong jet can create a symmetry, but it doesn't easily explain dual rotation patterns. Polion viewing geometry could create symmetries, but it doesn't account for why those symmetries would evolve and rotate over time in the specific way observed. Rhythmic outgassing from collapsing cavities is plausible in theory, but has never been documented with this degree of organization in any observed comet. The natural explanations are possible, but they require increasingly specific and unlikely conditions. This is what scientists call the stacking unlikelihoods problem. Any single anomaly can usually be explained by invoking some unusual but natural circumstance. But when you have multiple anomalies all present in the same object, you have to start stacking those unlikely explanations on top of each other, and the combined probability becomes strained. 3i Atlas isn't just showing unusual coma structure, it's also showing an antitail that we'll discuss in detail shortly. It's also exhibiting non-gravitational acceleration. It's also displaying a typical spectroscopic composition. Each of those individually might be explainable through natural but unusual circumstances. All of them together in one object starts to suggest something more fundamentally different about what 3i Atlas is. The global confirmation from Spain, Thailand, Japan and the United States accomplished something important. It moved the conversation from one person saw something weird to multiple independent observers are documenting consistent anomalous features. That's not proof of anything extraordinary yet, but it's proof that something real is being observed, something that requires explanation beyond dismissive hand-waving about artifacts and mistakes. The images show what they show. The question now becomes, what physical process explains what we're seeing? And as we're about to discover, that question becomes even more urgent when we examine one of the most persistently anomalous features appearing in these images, a feature that violates basic comet physics in ways that even the most generous natural explanations struggle to account for. On November 18th and 19th, NASA held a virtual event specifically to discuss 3i Atlas, observations from professional space-based instruments. This was the long-awaited official institutional response to the interstellar visitor that had been exciting amateur astronomers for months. Hubble Space Telescope had observed it. James Webb Space Telescope had conducted spectroscopy. Even Mars orbiters, spacecraft that happened to be in position to catch views during 3i Atlas's perihelion approach, had captured images. The anticipation in the astronomy community was high. Professional instruments worth billions of dollars, positioned above Earth's atmosphere, equipped with the most advanced optics and sensors humanity has ever built, surely they would provide definitive, crystal-clear imagery that would settle all the questions and speculations swirling around 3i Atlas's appearance. The images NASA released were disappointing. Not blank, not useless, but disappointing relative to expectations, and more importantly, disappointing relative to what amateur astronomers had already achieved from ground-based observations. Hubble's images showed a diffuse glow around what appeared to be a nucleus, but the detail was limited. JWST's contributions were primarily spectroscopic, chemical composition data, which was scientifically valuable, but didn't provide the visual clarity people were hoping for. The Mars orbiter images taken during perihelion approach were, to be blunt, fuzzy blobs. You could see that something was there, that an object existed, that it had a coma, but the structural details that ground-based observers were reporting simply weren't resolved in the space telescope images. This created an optics problem, and I mean optics in the public relations sense, not the telescope sense. How do you explain to the public that billion-dollar space infrastructure produced less detailed images of an object than backyard astronomers using equipment that costs less than a used car? How do you maintain institutional credibility when citizen scientists are outperforming your flagship missions? The professional astronomy community immediately jumped in with explanations, all technically valid, but the damage to public perception was already done. Let's be fair and examine the legitimate technical challenges NASA faced. First, observation windows. Space telescopes don't have unlimited access to any target. Hubble and JWST have packed schedules, with telescope time allocated months in advance to researchers who've submitted proposals for specific observations. You can't just pivot them to observe breaking targets instantly. By the time dedicated 3i Atlas observations were scheduled, the object's position and distance had changed and not favourably for detailed imaging. Second, solar conjunction issues. At certain points in 3i Atlas's orbit, it was positioned too close to the Sun from Earth perspective for safe telescope pointing. Space telescopes have strict sun avoidance requirements to protect sensitive instruments. That eliminated large observation windows. Third, distance and relative motion. Space is big, objects move fast, and capturing detailed images of something accelerating through the solar system requires precise tracking and timing. Those are all valid constraints. Professional astronomers weren't being negligent or incompetent. They were working within genuine technical limitations. But here's what that doesn't explain. Ground-based amateur astronomers faced many of the same challenges: distance, motion, atmospheric interference that space telescopes don't have to deal with, but which adds its own complications, and they still produced more detailed images. How? The answer is partly about timing and flexibility. Amateurs can observe opportunistically. If weather is good and the object is visible tonight, they observe tonight. They don't need committee approval or scheduled telescope time. They can take hundreds of exposures over multiple nights, selecting the best ones, stacking them for detail, processing iteratively until they extract maximum information. That rapid iteration and selection flexibility is harder to achieve with scheduled professional observations where telescope time is precious and strictly allocated. There's also a factor that's uncomfortable to discuss but important: institutional caution about releasing data that might be misinterpreted. NASA and professional observatories are acutely aware that anything they publish about unusual objects will be scrutinized, picked apart, and potentially used to support claims they don't endorse. If you release a highly detailed image showing structural features you can't immediately explain, you're inviting speculation. If you release a blurrier image where the features are less defined, you give yourself more interpretive flexibility. We need more observations to determine what we're seeing. That's not necessarily conspiracy or cover-up. That's institutional risk management in an environment where public misinterpretation of scientific data has real consequences for funding and credibility. But it's also the wrong instinct. Because when you release underwhelming images after a delay caused by a government shutdown, which itself created conspiracy theory fodder about whether the delay was really about administrative dysfunction or about controlling information release, and then amateur astronomers point to their own images saying, "Look, we got better data weeks ago, you've created a credibility vacuum." And credibility vacuums get filled with speculation, theories about suppression, accusations of gatekeeping, all the toxic dynamics that undermine public trust in scientific institutions. Avi Loeb was blunt in his criticism. His November 19th Medium post, published the day after NASA's virtual event, essentially said the images raised more questions than they answered, that the press conference's emphasis on "we're still analysing the data" felt evasive, and that the scientific community needs to be more transparent and responsive when dealing with objects that generate significant public interest. Loeb's quote, referencing Sherlock Holmes, was pointed. There is nothing more deceptive than an obvious fact. He was arguing that NASA's presentation treated 3I Atlas as obviously just a weird comet. Nothing to see here, move along. But the obvious fact interpretation requires ignoring the accumulation of anomalies that don't fit that neat category. To their credit, NASA's Planetary Defense Office clearly communicated one unambiguous fact. 3I Atlas poses zero threat to Earth. Its trajectory is well understood, is not going to impact us. For the segment of public concern focused on existential risk, that was the most important message, and NASA delivered it effectively. But for the segment of public interest focused on scientific mystery, what is this thing and why is it behaving strangely, the official response felt inadequate. The discrepancy between amateur and professional imaging also revealed something important about modern astronomy's ecosystem. We're in an era where equipment that once only existed in professional observatories is now accessible to serious amateurs. You can buy telescopes with apertures large enough to resolve significant detail on distant objects. You can attach cameras with sensors that rival what professional instruments used a decade ago. You can access processing software that implements sophisticated algorithms for noise reduction, stacking, enhancement. The democratization of astronomical technology means that citizen science isn't just amateur hour anymore. It's legitimate distributed observation capability that sometimes produces results competitive with or superior to institutional work. This should be celebrated as a triumph of technology and education, making cutting-edge science accessible to passionate enthusiasts. But it also creates tension. Professional astronomers spend years training, securing funding, accessing expensive facilities, and publishing through peer review. When someone with a telescope in their backyard produces data that challenges or outpaces official observations, the institutional response is sometimes defensive. There's skepticism about amateur processing techniques, about whether images have been overly enhanced or artifacts introduced. That skepticism is methodologically appropriate. All data should be scrutinized regardless of source, but it can come across as gatekeeping, as professionals dismissing work that doesn't come through traditional channels. The truth is that both amateur and professional observations have value and limitations. Professionals have access to capabilities, amateurs don't. Spectroscopy at wavelengths that require space-based instruments, coordinated multispectrum observations, computational resources for complex modelling. Amateurs have flexibility, geographical distribution, and sheer numbers that institutions can't match. The ideal approach is synthesis. Professional astronomers taking amateur observations seriously, amateurs understanding the constraints professionals work within, both communities collaborating transparently. With 3i Atlas, that synthesis hasn't fully materialized yet. The professional response has been cautious, emphasizing uncertainty and the need for more data. The amateur community has been more exploratory, willing to discuss anomalies openly even without having complete explanations. And scientists like Loeb are trying to bridge the gap, giving amateur observations serious analytical attention while maintaining scientific rigor. But NASA's underwhelming image release did accomplish one thing definitively. It meant that the primary detailed visual data about 3i Atlas's appearance was coming from amateur sources. That puts more weight on the Spanish, Thai, Japanese, and American observations we've been discussing. They're not just supplementary to official data anymore, they are the primary data for understanding the object's detailed structure. And that brings us back to the question, what exactly are those images showing? We've talked about geometric patterns and rotational features. Now we need to examine the most persistently anomalous feature, visible in images from both amateur observers and NASA's instruments. The one feature that appears in multiple independent datasets and violates the most basic physics we understand about how comets work. Here's something you probably learned in school, maybe in an elementary science class when you first heard about comets. Comets have tails, and those tails always point away from the sun. Always. It's one of the most reliable rules in solar system dynamics. Solar radiation, the stream of photons pouring out from the sun, exerts pressure on the dust and gas in a comet's coma, pushing that material outward, away from the source of radiation. It doesn't matter which direction the comet is travelling. It doesn't matter where Earth is positioned. The tail points away from the sun because physics demands it. That's been true for every comet humanity has ever observed, from ancient times when comets were omens and mysteries, through the modern era when we've sent spacecraft to rendezvous with them. Tails point away from the sun. It's fundamental. 3i Atlas has material pointing toward the sun. Not occasionally, not as a brief anomaly, persistently. Images from multiple observers across multiple observation periods show what astronomers call an antitail, a plume or stream of material extending sunward, directly violating the most basic expectation of cometary behavior. And before you ask, yes, astronomers have seen antitails before in rare circumstances. They're not unprecedented. But they're supposed to be optical illusions, geometric perspective effects that occur under very specific viewing conditions. They're not supposed to be real material actually flowing toward the sun, and they're definitely not supposed to persist for weeks across changing viewing geometries. Let's understand what a legitimate antitail is. Imagine a comet with a long tail streaming behind it, and by behind I mean away from the sun. Now imagine viewing that comet from a position where Earth happens to be aligned with the comet's orbital plane, looking edge-in at the tail. From that specific viewing angle, you might see what appears to be tail material on both sides of the comet's nucleus, the actual tail extending away from the sun, and an apparent antitail on the sunward side. But that sunward appearance is just perspective. You're seeing a portion of the tail that extends backward along the comet's orbit, which happens to curve toward a sunward position from your viewing angle. It's like looking at a curved road from a specific position, where part of the road appears to go the wrong direction even though it's actually continuous. These geometric antitails are known phenomena, they're understood, they're documented in standard comet physics textbooks, and they have specific characteristics that distinguish them from actual sunward flowing material. They appear only at certain viewing angles, they change or disappear as the viewing geometry shifts, and they're continuous with the main tail structure. You can trace the connection, seeing how the apparent antitail is just a perspective trick on the real tail. Actual material flowing toward the sun would require violating the physics of radiation pressure, unless something about the object or the material is deeply unusual. 3i Atlas's antitail doesn't cleanly fit the geometric illusion explanation. It was first clearly detected on August 30th, months before perihelion, and it's persisted through perihelion and into post-perihelion observations now extending into December. That's too long, across too many orbital positions and viewing angle changes, for a pure geometric effect. Multiple observers from different locations, meaning different viewing angles relative to the object, have documented the sunward plume. If it were a perspective illusion, observers viewing from significantly different angles should see different things. They're not. They're all seeing a sunward component to the material distribution. The presence of this feature in the Spanish, Thai, Japanese and American images we've discussed is one of the consistent elements across those observations. Ray Astronomy's processed images from Spain clearly show a directional asymmetry, with material extending toward the solar position. The Thai observations documented the same sunward component. AstroPhotoG's October 21st images from the United States, captured well before the November discussion about anomalies, show an asymmetric material distribution consistent with an antitail structure. These are independent observations from different viewing geometries, all pointing to the same conclusion. There's material on the sunward side of 3I Atlas that shouldn't be there according to standard comet physics. So how do we explain it naturally before jumping to exotic conclusions? One possibility. The material isn't actually flowing toward the sun, but being ejected from the nucleus in a direction that happens to be sunward due to the object's rotation and the location of active jets. If you have jets firing from specific active regions on the nucleus, and those regions rotate into positions where their ejection direction is sunward, you could temporarily create a sunward plume. The material would still be pushed back by radiation pressure once it dispersed into the coma, but near the nucleus, ejection velocity could overcome radiation pressure briefly. That's plausible. It could explain a temporary sunward feature, but it struggles to explain persistence. Rotation periods for comet nuclei are typically hours, not days. Any jet-driven sunward plume should appear and disappear as the active region rotates into and out of sunward-pointing orientation. Observers should see the antitail feature appear, fade, reappear in a rhythmic pattern matching the rotation period. There are hints of such variation in the data. Some observation periods show stronger antitail features than others, but the baseline presence persists more than simple jet rotation should allow. Unless the rotation period is unusually long, or there are multiple active regions all oriented to create sunward ejection, or the ejection velocity is exceptionally high. Another natural explanation invokes subsurface structure. If 3I Atlas has hollow regions or cavities beneath its surface, those voids could channel volatile gases in specific directions as they erupt. Think of it like volcanic vents on Earth. The surface topography and subsurface channels determine where material emerges and its initial direction. If 3I Atlas's subsurface structure creates preferential pathways for gas ejection in sunward directions that could sustain an antitail feature. This explanation has the advantage of accounting for persistence. Subsurface structure doesn't change quickly, so the directional bias would remain across multiple rotation periods, but it requires a very specific and unusual internal configuration that we have no direct evidence for. Here's where the rotation pattern connection becomes significant. Remember those dual spin wave patterns Ray Astronomy documented? The ones showing clockwise rotational structure in the coma gas? Those patterns have a directional axis, and observers analysing the full set of images have noted that the antitail feature aligns with the rotational axis of the spin wave patterns. They're not randomly oriented relative to each other. There's geometric correspondence, suggesting they're related phenomena driven by the same underlying cause, most likely the object's rotation and internal structure. If 3I Atlas has an unusually strong, coherent rotation, meaning it's spinning as a relatively solid body rather than a loosely bound rubble pile, and if its shape or composition creates directional asymmetries in how it outgasses, then you could potentially get both the organised rotation patterns and the persistent antitail from the same physical configuration. That would still be natural, but it would require 3I Atlas to be significantly different in structure and composition from typical comets, which tend to be loosely consolidated, irregularly shaped, and mechanically weak. And here's where the story gets stranger and more compelling. 3. The Atlas isn't the only comet showing an anomalous antitail. Comet R2 Swan, a completely different object with a completely different origin, is from the Oort cloud at the outer edges of our solar system, not interstellar space, has developed similar features. R2 Swan has shown persistent sunward plumes that don't fit geometric antitail explanations either. The two objects have nothing in common except that they're both comets, and they're both exhibiting the same anomalous behaviour at roughly the same time period. That parallel development is fascinating and troubling. Fascinating because if two unrelated comets are showing the same anomaly, it suggests we might be missing something fundamental in our models of cometary behaviour. Maybe there's a physical mechanism we haven't understood that operates under specific conditions, and both objects happen to meet those conditions. Troubling because it strains credulity to think two objects from entirely different origins would both exhibit the same rare anomaly simultaneously, unless something about current solar conditions is triggering behaviour we haven't seen before. Avi Loeb has suggested that the anti-tail feature, especially when correlated with the rotation patterns and non-gravitational acceleration we'll discuss next, could indicate directional mass ejection. Not random outgassing, but controlled or at least highly organised material release. In natural comets, that would require internal structure acting like nozzles or vents, channeling gas in specific directions. In artificial objects, and yes, we're entering speculative territory here, but that's where unusual observations force us. It could indicate propulsion systems, attitude control mechanisms, deliberate material release for course correction or momentum management. The natural explanation is uncomfortable because it requires 3I Atlas to be bizarre. A comet unlike any we've thoroughly studied, with internal structure and mechanical properties that create organised, directional outgassing persisting across months of observation. The artificial explanation is uncomfortable for obvious reasons. It requires us to seriously consider that an object travelling through interstellar space for potentially millions of years might have been constructed by non-human intelligence. Neither explanation sits comfortably within standard astronomical frameworks. But the observations don't care about our comfort. They show what they show. What makes the anti-tail particularly significant in the broader context of 3I Atlas anomalies is that it's not ambiguous. This isn't about seeing patterns in fuzzy images or interpreting subtle spectroscopic features. This is about material appearing on the wrong side of the object relative to the Sun. You can debate what's causing it, but the observation itself is straightforward. There's stuff where stuff shouldn't be, and when that observation appears in multiple independent datasets, persists across changing viewing geometries, and correlates with other anomalous features like rotation patterns, it becomes part of a larger puzzle that demands comprehensive explanation. We're stacking anomalies. That's what's happening here. Individually, each unusual feature might be explainable through natural but uncommon circumstances. The geometric patterns in the coma, unusual rotation, the anti-tail, atypical jet orientation, the spectroscopic composition, formed under different stellar metallicity. Each one, taken alone, gets a shrug and a nature as diverse explanation. But when they all appear in the same object, when you have to stack multiple unlikely explanations to account for everything, the cumulative improbability starts to matter. This is why Loeb has placed 3I Atlas at level 4 on his scale, and is seriously considering whether it crosses to level 5. Because level 5 isn't about any single smoking gun feature. It's about the convergence of multiple anomalies to the point where extraordinary hypotheses become mathematically comparable to stacked unlikely natural explanations. And we haven't even discussed the most quantitatively significant anomaly yet, the one that professional astronomers track with extreme precision because it's not subject to interpretation or processing techniques, the one that shows up in pure orbital mechanics and can't be dismissed as visual artifacts or perspective effects. Orbital mechanics is one of the most precise sciences we have. When we track an object moving through space, we're measuring something governed by gravity, one of the fundamental forces of nature, mathematically described with exquisite precision by equations that have been tested and confirmed across centuries of observation. We can predict where planets will be decades in advance. We can calculate spacecraft trajectories that insert probes into orbit around distant worlds after years of flight, arriving within seconds of schedule. We're good at this, really good. So when an object's actual trajectory deviates from its predicted gravitational path, we notice, and we demand explanation. 3I Atlas is not following a purely gravitational trajectory. Starting around its perihelion passage on October 29th, positional measurements began showing deviations from the predicted path. The object is accelerating in ways that gravity alone doesn't explain. This is called non-gravitational acceleration, and before we get ahead of ourselves, yes, it happens with regular comets too. It's not automatically anomalous, but the characteristics of how and when it's happening with 3I Atlas are raising questions that don't have easy natural answers. Let's establish what normal non-gravitational acceleration looks like in comets. When a comet approaches the Sun and its surface ices begin to sublimate, gas erupts from the nucleus. That erupting gas carries momentum. If the gas erupts symmetrically in all directions, the momentum cancels out and the comet's trajectory isn't affected. But comet nuclei are irregular shapes with uneven surface composition and rotation, so gas eruption is almost always asymmetric. More gas comes off one side than the other. That asymmetry creates a net thrust. Think of it like a very inefficient randomly oriented rocket engine. The comet gets pushed slightly off its purely gravitational orbit. Astronomers have documented this in hundreds of comets. It's expected. It's normal. The key characteristics of normal cometary non-gravitational acceleration are that it's relatively small in magnitude, it's linked to solar heating intensity, meaning it increases as the comet approaches the Sun and decreases as it moves away, and it's irregular or chaotic because the surface properties and rotation create unpredictable variations in where gas erupts most strongly. Astronomers can model typical magnitudes based on the comet's size and activity level. Deviations are usually within expected ranges for objects of a given type. 3. The Atlas's non-gravitational acceleration has features that are challenging to reconcile with standard cometary behavior. The timing is one issue. Precise measurements showing significant deviation from the gravitational path emerge most clearly around perihelion, which is when you'd expect maximum thermal activity and outgassing, so that part makes sense. But the pattern and magnitude of the acceleration don't cleanly match standard models. Avi Loeb, in his November 27th updated analysis, argued that the positional measurements are showing acceleration with tighter constraints, more precision, meaning the deviation is more definitely real and not just noise in the tracking data, than skeptics have acknowledged. Here's where a scientific controversy emerges that's worth understanding. In astronomy, when you measure something, you always have uncertainty, measurement error, instrument limitations, the inherent difficulty of tracking a moving object millions of miles away. That uncertainty is quantified using statistical methods, often expressed as sigma levels. A 1 sigma detection means there's about a 68% chance the signal is real and not just statistical fluctuation. 3 sigma is about 99.7%. 5 sigma, the gold standard for claiming a discovery in physics and astronomy, means there's a 99.9999% chance the signal is real. For 3, Atlas's non-gravitational acceleration, the debate between Loeb and other astronomers has centered on what sigma level the measurements actually reach. Loeb has suggested the precision might be reaching very high sigma levels for some components of the acceleration, indicating it's definitely real and definitely unusual. Skeptics, including astronomer Matt Wright, who's publicly debated Loeb on this, argue the measurement precision isn't that tight, that the uncertainties are larger than Loeb claims, and that the observed deviations are within the range you'd expect from a somewhat active but otherwise normal comet. This isn't a debate about whether the acceleration exists. Both sides agree it does. It's a debate about whether it's quantitatively unusual enough to warrant calling 3I Atlas anomalous. The technical details get complex, involving orbital fitting algorithms, covariance matrices, observational cadence, astrometric precision, all methodology that requires expertise to evaluate properly. For our purposes, what matters is that there is a genuine scientific debate about how unusual the acceleration is, which means we're not in everyone agrees this is weird territory yet. But we're also not in this is easily explainable territory. We're in the uncomfortable middle ground, where the data is ambiguous enough that scientists with different priors, different baseline assumptions about what's likely, reach different conclusions. What's not debated is that the acceleration exists and that its timing correlates with other anomalous features. The acceleration pulses, variations in magnitude over time, appear to align with rotation period estimates derived from the coma structure observations. That correlation is exactly what you'd expect if the acceleration is being driven by directional outgassing from active regions that rotate into and out of favourable orientation. It's what you'd predict from a natural mechanism. But it's also what you'd predict from a technological mechanism, a propulsion system that fires in pulses, or attitude control thrusters that activate periodically. This is the frustrating aspect of analysing 3I Atlas. Almost every anomaly has plausible natural explanations that would be unusual but not unprecedented, and those same anomalies also have artificial explanations that would be extraordinary but not impossible. The data doesn't cleanly distinguish between very weird comet and artificial object. What it does clearly establish is that something about 3i Atlas doesn't fit standard templates. The question is how far outside those templates it really is. There's historical precedent here that everyone thinking about 3i Atlas is aware of. Oumuamua, the first interstellar object we discovered, back in 2017, exhibited non-gravitational acceleration that sparked enormous controversy. Oumuamua's acceleration didn't match the expected pattern from cometary outgassing. It was too strong relative to the observed dust and gas emission. It had the wrong directional characteristics, and it persisted in ways that seemed inconsistent with thermal-driven sublimation. Loeb famously proposed that Oumuamua's acceleration could be explained by solar radiation pressure acting on a thin artificial structure, essentially a light sail, something built rather than natural. That hypothesis was and remains controversial, with most astronomers arguing that unusual but natural degassing mechanisms could explain the data without invoking artificial origins. We don't need to resolve the Oumuamua debate here, but it's relevant because it established the template for how the scientific community reacts to interstellar objects showing unusual behaviour. There's deep institutional resistance to artificial hypotheses, which is methodologically appropriate. Extraordinary claims require extraordinary evidence. But there's also acknowledgement that we can't assume interstellar objects will behave exactly like solar system objects. They formed under different conditions, around different stars with different compositional and structural characteristics. Some degree of strangeness is expected. The challenge is determining when strangeness crosses from interestingly unusual to demands extraordinary explanation. For 3i Atlas, the non-gravitational acceleration adds another piece to the puzzle. By itself, it might just indicate an active comet with asymmetric outgassing. Combined with the organised coma structure, the persistent antitail, the unusual composition, and the multi-observer confirmation of geometric features, it becomes part of a pattern that's harder to dismiss as routine variation in natural objects. Each anomaly reinforces the others, creating cumulative evidence that something genuinely atypical is happening. There's also a predictive component here that makes the non-gravitational acceleration particularly important. If 3i Atlas is exhibiting propulsive behaviour, whether from natural jet-like outgassing or from something more exotic, then its future trajectory should show continued deviations from purely gravitational predictions. We can test this. 3i Atlas is heading toward a relatively close pass by Jupiter in March 2026. Jupiter's massive gravity will significantly alter the object's trajectory, and by measuring exactly how that trajectory changes, astronomers can refine their understanding of any non-gravitational forces acting on the object. Loeb has explicitly predicted that observers should watch for trajectory changes near Jupiter that might indicate more than passive gravitational deflection. If 3i Atlas shows course corrections that look controlled, that respond to the Jupiter encounter in ways that seem intentional rather than random, that would be extraordinary evidence. Of course, natural mechanisms could potentially produce such behaviour too, if the thermal conditions near Jupiter trigger specific outgassing responses. But the Jupiter encounter represents a test, an opportunity to gather data that might distinguish between competing explanations. There's even been discussion about whether NASA's Juno spacecraft, currently in orbit around Jupiter, might be positioned to observe 3i Atlas during the March encounter. Juno's instruments could provide detailed imaging and spectroscopy from a perspective and distance that ground-based observations can't match. Whether Juno will be tasked with such observations depends on operational priorities and orbital geometry. But the possibility exists for professional instrumentation to provide definitive data about this object at a critical moment in its journey through our solar system. For now, the non-gravitational acceleration remains a data point that doesn't resolve the mystery but deepens it. It's another anomaly added to the pile, another feature requiring explanation that doesn't fit neatly into standard categories, and when you combine it with the visual anomalies, the compositional oddities, and the multi-observer verification, you arrive at the question that's driving all this investigation. Is 3i Atlas unusual enough, anomalous enough, strange enough across enough different measurements to justify moving beyond "this is a weird comet" and into "this might be something else"? That's the level 4 versus level 5 distinction on the Loeb scale, the threshold where technological origin becomes a hypothesis that has to be taken seriously, not just speculated about on the internet. There's something elegant about spectroscopy. You take light, photons that have travelled millions of miles from an object, and you split that light into its component wavelengths. Each chemical element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint. By reading that fingerprint, you can determine what something is made of without ever touching it, without sending a probe, without even knowing where it is beyond that it's emitting or reflecting light. Spectroscopy is how we know the composition of distant stars, how we detect molecules in planetary atmospheres light years away, how we identify the material in comet comas, is one of the most powerful tools in astronomy, and it's been applied extensively to 3I Atlas. What it's revealing is strange. Not inexplicable, but strange. 3I Atlas's chemical composition is substantially different from typical solar system comets, in ways that tell us something important about where it formed and under what conditions. The James Webb Space Telescope spectroscopy showed that the object is unusually rich in carbon dioxide but has low water ice content. That's backwards from what we normally see. Solar system comets are typically water ice dominant. Water is the most common volatile in the outer solar system where comets form. Carbon dioxide is present but usually secondary. 3I Atlas inverts that ratio, suggesting it formed in a region where carbon dioxide ice was more abundant than water ice, a condition that requires either very cold temperatures or unusual chemistry in its parent star system. But the more striking compositional anomaly appeared in late August observations. On August 26th, spectroscopic measurements showed a steep rise in cyanide and nickel vapor emission from 3I Atlas's coma, but with notably weak or absent iron signatures. Nickel and iron are sibling elements chemically. They're both metals, they often occur together in cosmic material, they have similar properties. When you see metal emission from comets, iron typically dominates or at least appears alongside nickel at comparable levels. In 3I Atlas, observers were seeing strong nickel with minimal iron. That's backwards. It's not impossible. Nature is diverse, and formation conditions can create unusual elemental ratios, but it's atypical enough to demand explanation. Keck Observatory imaging in late August and September captured the spatial distribution of this nickel and cyanide emission around the nucleus, showing it wasn't just trace contamination or measurement error, it was real, substantial emission dominating the coma's metal content. By October 1st, during the approach to perihelion when solar heating was intensifying, the nickel production reached what observers described as extreme levels. The object was outgassing nickel-rich material in quantities that just aren't typical for comets we've studied. So what does unusual chemistry tell us? Chemistry is history. The elements and compounds in an object reflect the conditions where it formed, the temperature, pressure, radiation environment, available raw materials. Solar system comets formed in the outer regions of our solar system's protoplanetary disk, where water ice was the dominant volatile and the elemental composition reflected our sun's metallicity, the abundance of elements heavier than hydrogen and helium. 3I Atlas formed in a different star system, potentially around a star with different metallicity, potentially at a different distance from its parent star where different ice is condensed, potentially under conditions we can only infer. The high carbon dioxide, low water signature suggests formation in a very cold environment or around a star where carbon chemistry dominated over oxygen chemistry in the planet-forming disk. The nickel-dominant iron-poor composition is harder to explain naturally, but might indicate that the parent star had unusual nucleosynthetic history. Maybe it formed from material that had been processed through specific types of supernovae or stellar evolution that enriched nickel relative to iron. These are exotic scenarios, but the universe is big and stellar evolution is diverse. Not every star system has the same composition as ours, so attributing 3I Atlas's unusual chemistry to exotic but natural formation conditions is reasonable. But there's another interpretation, one that enters speculative territory, but that scientists like Loeb have mentioned. Composition can be engineered. If you were designing an object to travel through interstellar space for millions of years, you'd choose materials based on properties, durability, resistance to erosion from cosmic rays and interstellar medium, thermal stability, maybe even specific optical or mechanical characteristics. A nickel-rich composition would make an object structurally more coherent, more resistant to fragmentation, denser and more mechanically stable than a typical ice and dust comet. It's also highly reflective, which affects how radiation pressure and solar heating affect the object. We're not saying 3i Atlas was designed, we're saying that composition matters for both natural and potential artificial explanations, and the unusual composition we're seeing does have implications for how the object behaves. There's also polarimetric data to consider. Polarimetry measures how light is polarized, how the electromagnetic waves are oriented, which tells you about the surface properties and particle characteristics of reflecting material. Observations of 3i Atlas showed negative polarization, which typically suggests a mixture of icy and dark material, possibly with fine dust particles. That's consistent with a comet having both ice and rocky components. But the specific polarization values, when combined with the spectroscopic composition, create a profile that's unusual, not unprecedented, but outside the typical ranges for solar system comets. What matters most about the spectroscopic anomaly is how it connects to the structural anomalies. If 3i Atlas has a nickel-rich composition making its nucleus denser and more coherent, that directly affects how it fragments, or rather, why it hasn't fragmented. Most comets that undergo the thermal stress. 3i Atlas experienced at perihelion show fragmentation, or at least significant structural changes. 3i Atlas has maintained coherence. A denser, more mechanically robust nucleus would explain that persistence. It would also explain why the rotation patterns in the coma appear organized rather than chaotic. A coherent body rotating as a solid unit produces more organized outgassing than a loosely bound rubble pile tumbling unpredictably. The composition also affects the object's appearance and reflectivity. Nickel-rich surfaces have different albedo, reflectiveness, than typical comet surfaces, which are usually very dark, covered in organic material and dark silicates. If 3i Atlas has higher metal content, it might reflect light differently, which would affect how it appears in images and potentially how easy it is to observe. Some of the unusual features observers have noted, the specific way light scatters in the coma, the contrast between different regions, could be influenced by atypical composition. There's an important methodological point here. Spectroscopy is one of the least ambiguous types of astronomical data. When you measure emission lines from specific elements, you're not interpreting fuzzy images or relying on models with uncertain parameters. You're measuring wavelengths of light that directly correspond to atomic transitions. If you see strong nickel emission, nickel is present. There's no debate about interpretation. The debate is only about what the presence of that composition implies for the object's origin and nature. That makes spectroscopic anomalies particularly significant in building a case that something unusual is happening. You can't dismiss strong nickel, weak iron as a processing artifact or observer bias. It's in the data, unambiguously. Connecting the composition to the broader pattern of anomalies, we have an object with unusual chemistry, suggesting exotic formation conditions, or unusual structural composition, exhibiting organized geometric patterns in its coma that typical comets don't show, displaying a persistent antitail that violates standard physics expectations, undergoing non-gravitational acceleration that doesn't cleanly match typical cometary behavior, and confirmed by multiple independent observers across different locations using different equipment. Each anomaly individually might be explainable. The convergence of all these anomalies in a single object starts to look less like coincidence, and more like the signature of something fundamentally different from standard comet templates. This is exactly the situation where the Loeb scale becomes useful. It provides a framework for saying this object has accumulated enough anomalies across enough independent measurements, verified by enough independent observers, that it warrants serious investigation beyond routine categorization. Level 4 is where 3i Atlas currently sits. Anomalous, requiring investigation, not explained by standard models but not definitively requiring extraordinary explanations either. The question now is whether the totality of evidence pushes it to level 5, where extraordinary explanations become mathematically competitive with stacked unlikely natural explanations. Here's where we are. We have an interstellar object, the third ever confirmed, that passed through perihelion and is now moving away from our Sun, heading toward a Jupiter encounter in a few months. Multiple amateur astronomers across Spain, Thailand, Japan, and the United States have captured images showing geometric structure in its coma, organized rotation patterns, persistent asymmetries, and an antitail that shouldn't exist according to standard comet physics. Professional spectroscopy reveals unusual chemistry, high carbon dioxide, low water, nickel-dominant metal emission with weak iron. Orbital tracking shows non-gravitational acceleration that doesn't cleanly match typical cometary behavior. And NASA's official observations, while technically valid, provided less visual clarity than ground-based amateur work, creating a credibility gap and leaving the amateur images as the primary detailed visual record of this object. Each individual anomaly has potential natural explanations. Coma structure could be unusual rotation effects, antitail could be geometric illusion or a typical jet orientation. Composition could reflect exotic but natural formation conditions. Acceleration could be asymmetric outgassing. The problem is that explaining all of these anomalies naturally requires stacking multiple unlikely circumstances on top of each other. 3 Atlas would have to be an unusually dense, coherent nucleus with a typical composition and unusual rotation geometry, creating organized outgassing in patterns that persist across changing conditions, all while happening to exhibit spectroscopic signatures that are rare but not impossible. That's possible. Nature is capable of producing rare combinations of features. The universe is big, and we've only studied a tiny sample of objects. But at what point does stacking unlikely natural explanations become less parsimonious than considering alternative hypotheses? This is the central tension in the scientific debate around 3I Atlas. Avi Loeb has built a career on arguing that the search for extraterrestrial intelligence and the investigation of potential techno-signatures, signs of technology from non-human civilizations, should be pursued with the same rigor and openness as any other scientific question. His Loeb scale is an attempt to create a structured framework for evaluating astronomical objects that show unusual characteristics without immediately polarizing into its nothing versus its aliens camps. The scale acknowledges that most anomalies are natural, that extraordinary claims require extraordinary evidence, but also that dismissing possibilities prematurely because they're uncomfortable or unconventional is itself unscientific. Level 4 on the Loeb scale represents anomaly requiring further investigation. It's where an object has multiple unexplained behaviors that don't fit standard models but haven't yet reached the threshold where technological origin is a leading hypothesis. It's the zone of serious scientific attention without extraordinary claims. Level 5 is meeting potential techno-signature criteria, the threshold where the convergence of anomalies, the failure of natural explanations to account for all observations, and the statistical improbability of the observed combination of features makes technological origin a hypothesis that has to be considered seriously, not proven, not even most likely, but mathematically non-negligible, a possibility with enough evidential support that it can't be dismissed without direct investigation. Loeb has publicly stated that 3I Atlas currently sits at level 4, but that it's approaching the boundary with level 5. What would push it across? Additional observations confirming the patterns we've discussed, especially if the December visibility window produces more detailed imaging showing persistence of the geometric features. Stronger confirmation of the non-gravitational acceleration's unusual characteristics, better orbital tracking, tighter statistical constraints, correlation with rotation and activity patterns. Any observation during the March-Jupiter encounter that suggests non-random response to the gravitational environment, or discovery of additional anomalies we haven't yet detected, maybe spectroscopic signatures that are difficult to explain naturally, maybe radio emission or other signals, maybe behavioral changes that look responsive rather than passive. It's important to understand what level 5 does not mean. It does not mean this is definitely artificial. It does not mean scientists have proven non-human technology. It means the evidence has accumulated to the point where that hypothesis deserves serious investigation with dedicated resources, not just dismissal or marginal attention. It means the object should be priority targeted for follow-up observations with the best instruments available. It means publications exploring technological hypotheses should be considered legitimate scientific contributions rather than fringe speculation. Level 5 is about opening a door to investigation, not claiming to have already walked through that door and found answers. There's institutional resistance to that door opening, understandably so. The history of false alarms in SETI and technosignature research has made the scientific community extremely cautious. We've had pulsar discoveries initially thought to be alien beacons, only to realize they were natural neutron star phenomena. We've had spectroscopic anomalies in exoplanet atmospheres that looked like industrial pollution, only to be explained by abiotic chemistry. Every time the scientific community gets excited about a potential technosignature, and it turns out to be natural, credibility erodes. Funding becomes harder to justify. The field gets stigmatized. So the threshold for taking technological hypotheses seriously is deliberately high, and that's methodologically appropriate. But that caution can also become bias, a predisposition to explain away anomalies through increasingly strained natural mechanisms rather than admit that we might be seeing something genuinely unprecedented. Loeb's argument, which he's made repeatedly in the context of Oumuamua and now 3i Atlas, is that the burden of proof should be symmetric. If you claim an object is natural, you need to account for all its observed properties through plausible natural mechanisms. If you claim an object might be artificial, you need extraordinary evidence. Both claims require justification. You can't just default to natural explanation and declare victory while leaving multiple anomalies inadequately explained. So where does the evidence actually stand? Let's inventory the stacking anomalies. First, geometric structure in the coma confirmed by multiple independent observers using different equipment from different locations. This is real, not artifact, though interpretation remains debated. Second, dual clockwise rotation pattern suggesting organized rather than chaotic outgassing. Unusual but potentially natural if the nucleus has specific structural properties. Third, persistent anti-tail violating basic radiation pressure expectations, possible through geometric illusion or atypical jet orientation, but not cleanly fitting those explanations across all observations. Fourth, non-gravitational acceleration with timing and characteristics that don't perfectly match standard cometry models. Exists, but magnitude and significance are scientifically debated. Fifth, unusual spectroscopic composition with nickel-dominant metal emission and carbon dioxide richness, atypical but attributable to exotic formation conditions. 5 anomalies, each potentially explainable naturally. Convergence creating cumulative improbability. If you calculate the odds, not rigorously, because we don't have precise probabilities for each feature, but conceptually, you're multiplying rare events together. If each anomaly individually has, say, a 10% chance of occurring naturally in any given comet, and some are rarer than that, then having all 5 in one object is much less than 10%. This is informal statistical reasoning, but it captures the intuition. Multiple independent rare features appearing together is rarer than any single feature alone. At some point, the combined improbability becomes significant enough to warrant considering alternative explanations. Loeb has also placed a personal bet on this topic, which is worth mentioning because it shows his conviction level. In late November, he publicly wagered $1,000 that will have confirmed detection of alien visitors, whether through technosignatures in astronomical observations or other evidence, by 2030. That's within 5 years. That's not a safe bet if you think the probability is negligible. It's a statement that Loeb believes the evidence is pointing in directions that the broader scientific community will eventually have to acknowledge. Whether he's right or overconfident is something time will test, but it's relevant context for understanding his evaluation of 3i Atlas. He's not casually speculating. He's staking reputation and money on predictions derived from his analysis. The December 19th visibility window is approaching. That's when 3i Atlas reaches peak observability from Earth for the next several weeks before its position and distance make detailed imaging more difficult. Astronomers around the world are planning observation campaigns specifically to capture more data during this window. Better spectroscopy, higher resolution imaging, coordinated observations from multiple locations to eliminate geometric ambiguities. The data gathered in mid to late December will either strengthen the case that 3i Atlas is exhibiting anomalous behavior or provide natural explanations that resolve some of the mysteries. This is science in real time, hypothesis testing in progress. Then comes March 2026 and the Jupiter encounter. This is potentially the most significant observational opportunity. Jupiter's gravity will alter 3i Atlas's trajectory substantially. That's unavoidable physics. But exactly how the trajectory changes and whether there are any course corrections or behavioral changes during the encounter could provide definitive evidence about whether the object is purely passive or exhibiting any form of active trajectory control. If 3i Atlas shows changes that look intentional, that respond to the Jupiter environment in ways that seem purposeful rather than random, that would be extraordinary evidence. Natural mechanisms could still potentially explain such behavior. Maybe the thermal and radiation environment near Jupiter triggers specific outgassing responses that happen to alter the trajectory favorably. But at that point, you're reaching for increasingly specific and untested natural mechanisms. There's even been discussion, speculative, not officially planned, about whether 3i Atlas might release smaller objects or exhibit changes in structure near Jupiter. If you were designing a probe to explore our solar system, Jupiter would be an obvious target of interest. The largest planet, dominant gravitational influence, fascinating magnetosphere and moon system. An artificial object might alter behavior near Jupiter in ways a natural comet wouldn't. Again, this is speculative. There's no evidence this will happen, but it's the kind of prediction that follows from taking the technological hypothesis seriously, making testable predictions about what you'd expect to observe if the hypothesis were correct, then checking whether those predictions are borne out. Loeb's scientific approach has always been to make predictions publicly, early, so they can be tested fairly. He did this with Oumuamua, predicting that if it were a light sail, we'd expect specific characteristics in its acceleration and rotation that could be checked against future observations. Some of those predictions were supported by subsequent analysis, others were ambiguous. He's doing the same with 3i Atlas, identifying observable signatures that would support or refute the technological hypothesis, then waiting to see what the data shows. That's how science should work. Competing hypotheses making different predictions, observations determining which predictions are correct. The level 5 question ultimately isn't about proving anything, it's about resource allocation and investigative priority. If 3i Atlas reaches level 5 on the Loeb scale, the practical implication is that it should be treated as a high-priority target for every available telescope and instrument. Space agencies should consider dedicating assets to detailed observation. Academic researchers should pursue publications analysing its properties from multiple theoretical frameworks. The object should be monitored continuously, not just periodically. We should be putting our best capabilities toward understanding it comprehensively. Whether that happens depends partly on scientific consensus, partly on institutional priorities, partly on whether the public and funding agencies consider this important enough to warrant resources. Right now, 3i Atlas exists in this liminal space, significant enough that serious scientists are paying close attention, strange enough that it's generating substantial discussion in astronomy communities, but not yet conclusively anomalous enough to force mainstream acceptance that we're seeing something unprecedented. The coming months will likely resolve that ambiguity one way or another. Either additional observations will provide natural explanations that account for all the anomalies, allowing us to reclassify 3i Atlas as a very unusual but ultimately natural comet, or the anomalies will strengthen, multiply, and resist natural explanation to the point where even conservative scientists have to admit something genuinely unprecedented is happening. That's where we are. That's what the images from Spain, Thailand, Japan, and the United States have shown us. That's why this matters beyond just another comet sighting. We're potentially witnessing something that challenges our understanding, either revealing that comets can be far stranger than we realized, or revealing that not every object traveling through our solar system is natural. Either outcome would be scientifically significant. Either outcome would reshape how we think about interstellar space, object formation, and the possibilities that exist in a universe we've only begun to explore. Closing, the investigation continues. Word count, 750 words. Here's what we know for certain. Something strange is happening with 3i Atlas, and the people who first brought it to widespread attention weren't professional astronomers with billion-dollar telescopes. They were amateur observers, people with backyard equipment, passion for the sky, and the patience to capture and process images carefully. Rayan, Spain, observers in Thailand and Japan, AstroPhotoG in the United States. These aren't names you'll see in NASA press releases, but they're the ones who documented the features we've spent this entire discussion examining. That matters. It's a reminder that in the modern era, with democratized technology and open communication, scientific discovery isn't limited to institutional corridors. Curiosity and competence can come from anywhere. We also know that uncertainty is uncomfortable but necessary. The question of whether 3i Atlas is an extremely unusual natural object or something else entirely isn't resolved. It might not be resolved for months, maybe years. We might never know definitively if we don't get the right observations at the right times. That ambiguity frustrates people who want clear answers, but it's also where discovery happens. If we already understood everything, there'd be nothing left to investigate. The fact that 3i Atlas is puzzling means we're at the edge of current knowledge, and that's exactly where science gets interesting. What shouldn't be lost in the speculation and debate is the science itself. Regardless of whether 3i Atlas ultimately turns out to be natural or artificial, we're learning. We're refining our understanding of how interstellar objects behave. We're testing our models of comet physics under conditions we've rarely observed. We're improving our observation techniques and coordination methods. We're demonstrating that global networks of amateur astronomers can produce scientifically valuable data that complements or even exceeds professional capabilities. All of that is valuable independent of the final answer about 3i Atlas's nature. December 19th is approaching. Telescopes around the world will be pointed at this object, capturing as much data as the observing conditions allow. If you're in the astronomy community, if you have access to equipment, this is your opportunity to contribute. Verify or refute what others have reported, add your independent observations to the growing dataset, make your images and processing transparent so others can check your work. That's how distributed science should operate. Openly, collaboratively, with healthy skepticism balanced by genuine curiosity. For those of you without telescopes, you're still part of this. You're witnessing science in progress, watching how the community grapples with anomalous data, seeing the tension between caution and exploration play out in real time. That's valuable in its own way. Understanding how science works, the messiness, the disagreements, the gradual convergence toward better explanations, makes you a more informed observer of all scientific claims you encounter. Not everything that seems anomalous turns out to be important. But some anomalies change everything. Distinguishing between them requires patience, evidence, and willingness to follow where the data leads. March 2026 will bring another critical test. The Jupiter encounter will either resolve some of the mystery or deepen it. We'll see how 3i Atlas responds to the strongest gravitational influence it's encountered since leaving its origin star system. We'll see whether its trajectory remains purely predictable, or shows any unexpected changes. We'll potentially get observations from different instruments at different angles, providing three-dimensional understanding we don't currently have. Whatever we learn will advance the investigation. Avi Loeb has his framework and his predictions. Other scientists have theirs. Amateur astronomers are contributing observations that neither could accomplish alone. The synthesis of institutional resources, independent analysis, and distributed observation is creating a picture of 3i Atlas that's more complete than any single approach could provide. That collaborative investigation, with all its tensions and disagreements, is exactly what we need for questions this complex. So stay curious, keep watching. If you have theories, share them, but ground them in the actual observations, not what you hope is true or fear might be true. If you're skeptical, maintain that skepticism, but direct it at all explanations equally, not just the ones that sound too strange to believe. If you're excited by the possibility that we might be seeing something unprecedented, channel that excitement into support for continued observation and analysis, rather than premature conclusions. 3i Atlas is still out there, moving through space at tens of thousands of miles per hour, carrying whatever secrets it holds. We're watching, we're learning. And whatever it turns out to be, cosmic accident, natural wonder, or something that forces us to reconsider our place in the universe, the investigation itself is making us better observers, better scientists, better thinkers. Subscribe if you want coverage of the December 19th observations and the March Jupiter encounter. Drop a comment with your theories or questions. I read them, and the community discussions often surface insights I haven't considered. Share this with anyone in your life who looks up at the night sky and wonders what's out there. Because right now, one of the strangest answers to that question is visible in our telescopes, and we're all watching together to see what it reveals. The investigation continues, and that's exactly where it should be.